Hello, thank you for joining us. Today, the IEEE Solid State Circuit Society are hosting a webinar. The topic of today's webinar is New Opportunities in Non-Uniform Sampling by Professor Mike Chen. After the presentation, there will be a Q&A. Please use the Q&A section on your dashboard to ask Professor Chen your questions. SSCS Webinar Chair Alvin Logue will be our Q&A moderator today. Mike Shuo-Wei Chen is an associate professor in the ECE department at the University of Southern California. As a graduate student, researcher at UC Berkeley, he proposed and demonstrated the asynchronous SAR ADC architecture, which has been adopted today for low-power, high-speed analog to digital conversion products in industry. At USC, he leads an analog mixed-signal circuit group focusing on data converters, frequency synthesizers, power amplifiers, transceiver design, computing circuit, and analog circuit design automation. Thank you for joining us today, Professor Chen. The floor is yours.
Thank you, Kelsey, for the kind introductions. And also, I would like to thank Elvin for the invitation for this seminar talk. So today, I'm going to talk about a new opportunities in non-uniform sampling. So this is basically a research adventure that we have been doing nearly almost a decade in the past. So today I'm just very happy to share, some of the lessons that we have learned and some, promising aspect, hopefully, that I can show to the community. Okay, so since we are talking about sampling, so I have to talk about Nyquist, right? So Harry Nyquist, he really established the foundations for the well-known Nyquist sampling theorem in 1920s, right? So here I list a couple seminal papers that he has published. So basically what Nyquist told us is that there is no loss of information when the analog or the continuous time signals is sampled at least twice of its highest frequency. The theorem was basically driven by the telegraph communication problems, in between World War I and World War II. Basically, that's the booming period of a lot of signal processing and telecommunications. So a lot of interesting, theories was basically, proposed and invented and completed during that time. So basically, Nyquist has really shaped the circuit design that we have been doing today. So as you can see here, this is pretty much the most ADC that we have been using today, right? I would say it's probably 99.9999% of the ADC that we have been using. Basically, we just follow what Nyquist has told us, right? So if, let's say, my input is a band limited signals, between fs over 2 on each side of the spectrums, then basically we know today that we need to sample these analog signals at least at the twice of the highest frequency, which means fs in this case. As you can see here, this shows the time domain waveforms. This is the analog waveform in the background, and then we try to sample at the uniform time grid. So you can see this red cross point. Those are the point that we are taking. Then basically, what we have been doing today for the A to D, so-called A to D converters, is to first take these symbols, and then next, we are trying to quantize this analog voltage into a discrete levels, right? The reason is that so that we can represent that in a digital code, as you can see on the right-hand side. So basically, no matter what kind of ADC topology that we are using today, we just basically try to optimize, how we do this voltage quantization, right? So there are many ways that we can do, and hopefully, we do it in a very power efficient way. So as you can see, no matter what kind of ADC topologies, you basically try to snap all those analog voltage level into the discrete quantization level. Okay, so the bottom line is that, when we are using this so-called uniform sampling, right? We sample the input at the uniform time grid. There's also a well-known phenomenon called frequency aliasing, right? So if those of you have taken this, classes in undergrad class in EE, I'm sure that, you have learned this, whenever you sample the signal at a particular rate as fs, and you are going to alias the signal at every integer multiple of fs. So this is basically a very fundamental limit that we have been dealing with whenever we design the so-called A to D converters today. Okay, but however, if we look back to the development of this Nyquist, theorem, there's one paper that I can find. If you go back to this is the 1956 papers, by Yen, right? So the paper title, as you can see here, is on non-uniform sampling of bandwidth limited signals. So here I circle some passages. This is in the introduction of his papers, where he cited a Black, a statement from Black, to Cauchy, right? So here I just want to go over this, right? Because this actually contains very important information. Basically, Black was saying that, if a signal is a magnitude and time information functions, right? So it contains the magnitude and time functions. And then if we divide the time into the subintervals, right? And then these intervals, t, will be less than half period of the highest frequency of the input. Okay, so basically, so far it's just follow the Nyquist, right? But the interesting message here is that, he go ahead and then and state that, if this sample is taken from each subinterval in any manner, okay, in any manner, then the knowledge about these signals, okay, about these simple signals, it actually contains all the information of the original signals. So basically, I translate that message. Basically what they're saying is that, as long as the average sample rate still meets the Nyquist rate, means that, it's still more than twice the highest frequency component, there is no loss of information. Okay, so again, this was the message that I could find, from 1956, and where he cite a message from this book, from 1953. Okay, so this is the earliest that I can find. So based on this message, it basically tells you that, hey, we don't necessarily need to follow sampling in the uniform time grid. So what does that mean? So here, it shows that, perhaps we can actually sample the input at irregular time. So basically it means that, your input can be sampled at the non-uniform time grid, right? So anything that is not uniform time grid is possible, right? So you can actually retain the original analog information. So sure enough, there are some, sampling techniques that have been proposed that sort of follow this concept, such as, random sampling, multi-coset sampling, level crossing sampling, and etc. Right? So there are different approaches. Basically, it's all following along the line that, you don't need to sample the input uniform grid, right? You can, sample at a different time. And then afterwards, you still, would need to do some form of amplitude quantization, just so that, you turn that into some discrete level. Okay, so the message that I'm taking here is that, because we are sampling at an irregular time, so remember previously I talked about whenever we do uniform sampling, there's always an aliasing at the integer multiple of fs. So basically, whenever we do non-uniform sampling, we are actually changing that aliasing pattern. Okay, and in a very extreme case, if you are doing this signal-dependent sampling, such as a level crossing, it can be actually alias-free. Okay, so there's no because there's no constant sample rate, so there's no longer a so-called frequency aliasing at integer multiple of fs. Okay, so that's pretty exciting, right? So basically it means that, hey, there are different ways of doing the sampling. It's not just focusing on the uniform sampling. So what's the problem? How come people are not doing that today? And I attribute that to probably the reason is because there's still a problem of how we can process those non-uniform samples, right? So it is true that the signal reconstruction is generally more complex, compared to uniform sampling, because the uniform sampling, you just take the sample and you just cascade them, right? You just basically just sort them out, in sequence, and then the digital processor will just process it. However, the message that I like to point out today is that even though the algorithm may be more complex or maybe more unknown, right? Because this is not compared to uniform sampling. It's a lot less people have been working on this. It actually presents a new opportunity, mainly related to that ADSing pattern, right? Because we do non-uniform sampling, it could be ADS-free, or it can be some weird ADSing patterns. So maybe there's something that we can take out of that. So in general, I look at the across the community, right? So there are a couple of approaches that you may be able to reconstruct the non-uniform samples, and I could categorize that into continuous time and discrete time, right? For the continuous time reconstruction approach, this one from Dr. Yannis group, they did a lot of fantastic work in the past. And then here I just list one list, but feel free to go to their website and see a lot more publication in the past. So they basically combine those non-uniform sample in a continuous way, right? So the output is still analog-ish, is still sort of a non-uniform at the non-uniform time or asynchronous time output. There's another approach which is discrete time, and this is really something that my group have been really focusing on pretty much nearly 10 years, right? And we really focus on both the algorithm side and also on the circuit implementation side, because we're still a circuit design group. So we feel more excited, whenever we see something that's working in the lab. So that's really what we have been trying to focusing on, and that's also something that I like to share with you guys today. Here, I also want to point out there are still a lot of researchers in the Signal Processing Society. They have been working on this non-uniform sampling in general, right? So they actually propose different schemes to how to take all those non-uniform samples and how you can possibly reconstruct that, right? So one of the information that I personally like is from Dr. Mavasti's book on the non-uniform sampling theory and practice. It basically, you can see a lot of researchers, they share their different algorithms that how you can construct the signals using those non-uniform points. Okay, so that's roughly about the background. So we sort of look at this problem just about 10 years ago, and the first sort of the block that we have been looking into is the ADC. So as you can imagine, ADC is probably one of the block that's mostly tied with the sampling, right? So you have to sample the input and then you have to quantize. So ADC is the block that we have been starting with. So shown here on the top, right? So this is a conventional ADC, which I showed you earlier, right? Basically, it contains the sampling and the voltage quantization, right? So remember, we want to quantize that to the discrete levels. But then, because the frequency ADSing, so any unwanted signals at those ADSing frequencies, unfortunately, it will all ADS back to the signal band, right? So therefore, today we know that, before your ADC, we almost always, right? Almost always have to use this analog anti-aliasing filter. Why? Because you really want to remove those unwanted signals present at those ADSing frequencies. Okay, but then also because of uniform sampling, as we know, if I send in a sine wave, the quantization noise coming from the voltage quantizers will all ADS back. So that's why you can see all those quantization noise will distribute between DC to FS over 2. And guess what? If we integrate all these energies, right? So will be exactly LSB squared divided by 12, right? The well-known LSB squared divided by 12 energy, right? So if you took any signal processing class or ADC class, I'm sure that you have learned about this, right? So that's the fundamental noise floor of the ADC. Okay, so again, look at the conventional ADC, we have filter, we have uniform sampling, and then we have voltage quantization. So when we started the project, we look at this non-uniform sampling, right? So the question we ask ourselves is that, how about this? why don't we shuffle around these blocks, right? So we still do the same thing. We try to convert the analog signal to the digital signals, right? And then we still want to convert back to the uniform digital samples, right? The reason is because today all the DSP chip, basically all the processor chip, unfortunately most of them are still taking the uniform samples, right, for the digital. So basically what we are trying to do is that we move the filter in the non-uniform domain, and we move the voltage quantization to the first block, right? And we still need this uniform sampling, but we push that to the very end. So you can see that we basically shuffle around the sequence of the A to D conversions, and look at what happened, right? So now, because I put the voltage quantization upfront, then if I sending a signal here, because this is a signal-dependent sampling, or so-called level crossing sampling, this voltage quantization noise, they will no longer ADS back, like what you have done, upfront here, right? When you do uniform sampling. So you basically will have this quantization noise will show up as a harmonics of the input signal. So you can see that, if this is F, then it will be 2F, 3F, 4F, and 5F, and all the way to infinity. So now here's the trick, right? So we know that, if we are going to do uniform sampling at the very end, eventually this frequency aliasing will happen. And that is true, right? So if you don't do anything, you just do voltage quantization and you just perform uniform sampling, unfortunately, it will be exactly the same as before, right? So all the noise will get folded between DC to FS/2. And therefore, we really have to do something in between, right? So this is really, I think, is one of the key excitement, of what we can do in the non-uniform sampling aspect. Which is we can have some filter, right? So if we can have some filters, and we can get rid of those, harmonic, that caused by this quantization. And then afterwards, even though I have, uniform sampling, there's nothing to fold it back, right? Because it's already get removed by this filter, right? So we were kind of excited about that because, basically what you were saying is that, this anti-aliasing filter, you no longer need to necessarily put that in the analog domain. You could do that in the digital domain. But this digital is kind of weird, right? Because this is not uniform, right? So you cannot just plug in MATLAB or any, digital FIR filters, to do this processing. This is kind of at the irregular time, right? So how can we do that, right? So that's really intrigued us, right? About 10 years ago. So what I did is that I went ahead, and did a quick MATLAB simulations, right? So here, I use a different bits output voltage quantization from 4 bit to 10 bit, and I try to put some filtering, right, in between that non-uniform sampling and the final uniform sampling, right? So that filter block. So I try to remove it. I do a very cheating way. I just try to remove it and just to say, hey, anything beyond a particular corner frequency, I'm going to remove it. I just want to see how much that we can gain, right? As you can see here, if you keep increasing the bandwidth of that filter, right, larger and larger, which means that you let all the quantization noise will fold it back to the signal band, right, after the uniform sampling. So that's why you see that no matter how many bit resolution you use in the quantizers, they all plateau to this certain levels. And these levels, as you can see, 4 bit right here, right, 5 bit right here, and if you calculate the value, it's pretty much come back to the well-known SNR equation, SQNR equation of the ADC, right, which is 6 times the number of bits plus 1.76 dB, right? So that's no surprise, right? Because as I said before, if we don't somehow do the filtering in between, right, in the non-uniform samples, basically we are getting nothing, right? Getting nothing. But however, if you actually do something, to remove those noise, and I was actually pleasant surprised that you can actually improve the SNR by a huge amount, right? So in the case of the 10-bit quantizers, you could actually improve as much as 30 dB, right? So so that's kind of exciting. We thought that, hey, maybe if we just figure out how to do that, there's perhaps something to begin here. And then of course the question is, how do we do that filter, right? So that turns out is basically a magic block, a black box. At least at the time, we didn't know how to do it. So in order to understand how we could do that, so we sort of step back and look at, the so-called discrete time filter category, because that's discrete time. So basically, we have 4 different possibilities, right? So in terms of amplitude, it can be continuous amplitude, it can be discrete amplitude, right? Because it's discrete time, so we also have 2 choices. One is uniform discrete time, and the other is non-uniform discrete time. Okay, so let's take a look, one by one. In the first quadrant, continuous amplitude and uniform discrete time. This is what we use today as a lot of switched capacitor circuits, right? Like a switch cap, filter, right? We just, take those samples, right? The uniform samples, and we just, add, subtract, in the analog domain, right? So that's a switch cap circuits. Very popular, used today, right? So everybody, I'm sure that many of you have designed one of those circuits in your career. A very powerful tool right there, right? And then in the second category is a discrete amplitude and uniform discrete time. So obviously this is all the digital signal processing that we use today, right? So like our digital filter, right? Our digital filter has a discrete amplitude and also uniform discrete time. Okay, so again, that's another thing that has been popularly used, adopted. And the third quadrant, it's possible that we do continuous amplitude and non-uniform discrete time. So this one, we're still working on it. We still haven't quite 100% figured out how we can do that. So basically what this is saying is that, when we turn this switch capacitor circuits, and we kind of turn that clock into some kind of a non-uniform clock. Okay. So I think it's possible, but I think that there's more potential that we can further explore, right? But today, I would be more focusing on the fourth quadrant here, which means the discrete amplitude, and the time will be non-uniform. Okay, so here we call that as a non-uniform DSP, because this is really still a digital samples. It's just that those digital samples, they are happening at irregular time. Okay. What really excites us is that, because the non-uniform sample, right, as I mentioned earlier, if you actually use a signal dependent sampling, you could actually have an ADS-free property, right? So that means that, it is actually a digital version of a true analog signal processing. So that's kind of interesting, right? So even though, we say that, hey, at least for myself, before I thought about ADS-free processing, I really have to, design that in the analog domain. But now it's really actually created new directions that maybe we can do something in that fourth quadrant. And secondly, sorry for the index. Secondly, because it's non-uniform, so we could actually interface with the synchronous digital domain, right? So we can remember that uniform sampling block at the very end. We can still turn that back to the uniform digital sample. And later on, I'm going to show you how we actually do that. And then we can still use all the DSP or the processor that you can get from the market. And more importantly, because that's digital, so you still can take the advantage of technology scaling. Okay, so those are the things that's kind of going behind our project, right? So we think that, hey, maybe there's something that we can do. Okay, so let me start to talk about how we actually do that filter in the non-uniform DSP domain. Okay, so let's start from the most straightforward one, right? So shown on the top, this is the analog filter, and then here I'm showing nothing fancy, right? It's just the simple RC filters, and supposedly give you some kind of low pass filter. So if you have a signal, what I show here as a red triangle, and let's say you also have some band limited noise associated with that, and then after the filter, you're gonna select your signals, and then you're gonna get rid of the so-called auto band noise, right? Because you filter that out. So afterwards, if you put a conventional ADC, which is uniform sampling ADC, what you're going to get is that you get your signal, so which is very nice, and you also get this one copy of the noise, right, which is the inside the band of that low pass filter. Okay, so nothing wrong with that. That's probably the most basic ADC that we've been doing. And for the second one, right? So if we don't use analog filter, right, we say, hey, you know what? Why don't we do just the traditional digital filter, right? Which means that we're gonna have the uniform sampling here, and we're gonna put this shown here is the FIR filter, right? The digital FIR filter. So as you can see here, because the input is uniform sampled, right? So each tap are also uniform, right? And the coefficient, you just design the filter response, and you can calculate, what's the coefficient. So let's say, I go ahead and design again a low pass filter, right? Just like on the top, right? The same bandwidth and same sharpness of the filters. Unfortunately, because the uniform sampling, there's an aliasing, right? Remember in the first slide, I showed you that there's gonna be frequency aliasing. So unfortunately, all this noise, which shown in the yellow box here, they were all folded back to in-band, right? So you're gonna fold in this case 3 times, right? So you will all added on top. So even though you're trying to do the filter, but however, the noise already folded back. So after the uniform sampling, right, you actually get a worse signal to noise ratio. Okay, so the last one, which is the one that we have been working on, is that we recognize that the uniform samples they will come in a irregular time, right? So it's no longer regular time. So, but I still like to make an analogy, right, to what we have known today about FIR filter. So essentially, the way I like to think about this is that we are designing a sort of a dynamic FIR filter. Okay, the reason why I call it dynamic FIR filter is that, as you can see here, the tap here is different, right? So the tap delay here is no longer at the uniform time grid, right? So it has a different time, like tau 1, tau 2, and so on, right? And you know what? Even the coefficient, we should also dynamically change, right, based on the non-uniform sample. So if you do that, it turns out that you could actually come up with the response that just mimic like a analog filter, and which means that there's no aliasing. You see that there's no aliasing at any rate. This is very different from the traditional uniform filter and a traditional digital FIR filter, where you can see it will be aliasing at the sample rate, right? So if you do that, as you can see, then I can still do something like a analog anti-aliasing filter, right? So I can still remove the noise out of band. And afterwards, again, we still want to convert back to uniform samples. So we put a uniform sampler, and we still get my desired signal, which is red triangle, and with 1 copy of the noise. Okay. So that's kind of interesting, right? So with this kind of sort of adaptive or dynamic filters, we can do something that's just like an analog filter. Okay, so the question is, how do we do this? Okay, so here I'll try my best to summarize just in one slide, and then I'm just going to give you a very, very high level description of how you can possibly do this, just so that you can take a look what does that take. So when we work on this, right, because we know this can be alias free, right, and then we want to do something really similar to a analog filter. So as we know, when we do analog filter, basically if you have an input x of t, right, and output y of t, basically what you do is just convolution, right? Nothing fancy. LTS system, we do convolution, and that's exactly how we derive this equation. So we really just naively derive this equation. They say, hey, it's convolution, and except that right now this x of t they come in with the non-uniform sample, right? So they come at different discrete level, and they also come at different time, right? So this is not non-uniform time, right? So it's no longer a uniform time. So if you derive this equation, right, and I think this is a fun exercise, fun homework exercise, so you can derive yourself. And you probably will also get to this equation. Basically, what this tells you is that these are the non-uniform samples, right? So you have the magnitude information and your time information, right? And then so we need to record the time, right? So that's a different thing about non-uniform sampling. You do need to know the time that you actually generate the samples. So once you know the time and you also know the magnitude, then you can actually do that convolution, and then you can do like this. So basically what you do is that, at every resample point, so the resample point refer to the final stage uniform sampling. Remember I showed you earlier, right? So I do first non-uniform sample, right, filter, and then I have the final stage uniform sampling. So these are the uniform sample, right? So this slide, clearly show you how you can actually convert from non-uniform to uniform time grid, right? So what you do is that, at every resample time point, what you need to do is just that, you find the time difference, between all the non-uniform samples to your uniform resample point, right? So here I annotate as a different delta t, right? Then what you do is just that, you integrate the filter response, between those non-uniform time interval, and that's it, right? So this would correspond to that, what I showed you in the previous slide. This would correspond to that adapted filter coefficient, right? And then this you need to multiply by the magnitude of that non-uniform samples. So that's kind of interesting. So basically, this is somewhat echo back to what Black has been telling Cauchy, right? So the signal is a magnitude and time function, right? So this is exactly what it is, right? So now you can see we are representing the signal as a magnitude and time function. So the output, we are actually just using both information, right? We need to use the time information and the magnitude information, and we can compute that. Okay. Later on, I'm gonna show you some, of our silicon prototype, how we actually do this. But just to let you know, once you know the time, right? So you have this filter response that you're trying to achieve. You can actually pre-compute this, right? So if you have been working on the DSP part, there's a pre-computing circuitries that you can potentially do, right? So you can pre-compute it, the result, and you can just based on the time interval, and you can read out that coefficient. So that's basically it, right? So that's at least to my own surprise that it's actually, at least conceptually, it's not that difficult to understand, how you actually convert the signal back to the uniform domain, right? By using the time information and the magnitude information. And as you can see here, if you like to have a reconfigurable filter, right? So today people use a lot of reconfigurable filter. They want to use a different response. No problem. All you need to do is just to replace this term, and then you can compute different coefficient, right? So that's actually pretty nice. Okay. So once we realized that, we still didn't feel very comfortable, because as to build a circuit like that, it's actually a lot of investment. So in 2012, we actually built some discrete prototype, just so that we can test that algorithm, right? As you can see, we just went ahead and buy those comparators that can help us to do the voltage quantizations, right? And then what we do is that we capture the output and we send to the logic analyzers. And by using the logic analyzers, we can find the magnitude information and also the time information. Okay. Then what we do is that we take those samples. So by the way, everything is post-processing, right? So that's really the first time that we were trying to make a discrete prototype. So we take those samples and we put that into MATLAB, right? And then we just plug in the algorithm that I just showed you, right? Very naive algorithms, to have this magnitude and time information, and we compute that. And turns out it does actually attenuate the unwanted signal. So in this case, we actually try to synthesize a bandpass filters, and then we try to see whether we can knock down that so-called unwanted signals, right? And then this, as you can see, I can attenuate that by as much as 80 dB, and then you can see that it's actually very close by. So that's pretty interesting, right? So that gives us a little bit of confidence here, right? Just to show that hey, maybe there's something that we can do here, in the non-uniform sampling, and of course, here, compared to the ideal MATLAB models, your noise floor is a bit higher, obviously because this is real circuits, so there's gonna be a little bit more noise. But by and large, it's kind of matches to what we are hoping to see, right? So we're pretty happy about that. So because of that, we went ahead and built this so-called flash-based non-uniform sampling ADC prototype. Okay, for those of you who have built a flash ADC before, this really looked like a flash ADC, except that I need to point out, you look at these comparators, right? These comparators, they don't have clock, right? Because we are only doing the voltage quantizations, right? So we only try to detect, when does the signal will pass through the particular level, right? So this is a continuous time comparator, essentially, right? And then you are just comparing your input to a bunch of different levels, right? So you can see the input coming in, and you just compare it to different voltage levels. But then, because afterwards we really need to find out what's the time that you actually generate that non-uniform samples. So therefore, whenever you compare the trigger, we actually have to generate some pulses, right? Some pulses. Why? Because that pulses has to trigger a time quantizer, right? So that's actually a very important difference, between the conventional ADC versus this so-called non-uniform sampling ADC. If you want to do the discrete time processing, we do need to use this time quantizer. So as you can see, from this sort of flash-like, front end, we can extract the magnitude information, and we can also extract the time information. Okay, so that's pretty much it, right? So nothing fancy, we just really try to extract both information. And then this is the type photo that I always show today, because this is probably the best quality of the type photo I have probably in my entire career. And thanks to Dr. Mike White, he really helped to take the photo of this chip. So you can see here the input coming in, and those are just a bank of comparators, and you generate the pulse, and then you have this time quantizer, and you send to the output. So that's it. And I do want to show you this. So this was the first time we see in the lab, right? So remember that we generate the pulses, so we were able to pull out those pulses, right? Whenever you have a non-uniform samples. So as you can see, this is kind of what we expect, for the this non-uniform sampling ADC. So you can see that, here when your signal would transition faster, then you would generate a lot more non-uniform samples. So you can see that there's a lot of sample get generated here. And then when your signal is not changing very much, as you can see, there are not that many sample get generated around this region. Okay, so we thought that's kind of interesting, right? So it's non-uniform samples. And then, we kind of did a similar exercise, right? So we basically take that, magnitude and time information, and we plug in that the algorithm that we have been doing, right? And then, yes, we still can see that, rejection on the unwanted signals. So in this case, we try both low pass filter, we try the band pass filter, and then we can see that we can knock down the blockers. So at that time, when we first, show to outside people, and they feel kind of weird, because, how does that work? This is like non-uniform, sampling. Are you sure you can do some communication, right? So in order to sort of convince them, this can actually do just like a traditional ADC, right? You can plug in and do just in the communication systems. So we decide to put in a modulate signals, right? So we're putting a 16 QAM signal to this non-uniform sampling prototype. And then we also intentionally inject a huge blocker right there, right? And then we also apply that filter, right? We call it the digital anti-aliasing filter, basically that filter in the non-uniform DSP domain. And we were able to actually knock it down, right? We knock down the blocker, and we can still receive the EVN of right around minus 27 dB. Okay, and as you can imagine, if we remove that filter, this is gonna be a horrible constellation, right? You basically cannot see anything. Okay. All right. So after we are done with the flash-based ADC, right? So we kind of ask ourselves, what's next, right? What can we do? So we kind of, look at, in the ADC that, everybody have been designing, in the past, right? Non-uniform sampling. After people, was doing the flash ADC, and if you want to further push higher resolution, people do the so-called subranging, right? So you have a coarse and fine. So we kind of ask ourselves, can we do a similar thing? it turns out, yes, you can actually also do a non-uniform sampling version of the Subranging ADC. So as you can see here, it is exactly the same argument, right? So we know that the difference between flash and Subranging ADC is that I can save the number of comparators, right? So you don't want to always do this 2 to the power of n number of comparators. That ends up too much. So you can do this coarse and fine, and by doing coarse and fine, you can actually reduce a lot of comparators that you need. And then also because this is non-uniform time point, so sampling. So what we did at that time was that we actually create something called the timeout period, right? So basically, once your coarse comparators cross a certain levels, and then we start to count the time, right? So within a timeout. So after some timeout point, if there's another non-uniform sample get generated on the fine ADC, then yes, we are going to take that sample. Okay, the reason we want to do this is because we want to control the average sample rate of this ADC. Now, if you remember the message that I showed you in that 1956 papers, right? They say that non-uniform sampling, you just need to meet the Nyquist rate of the average sample, right? The average sample rate, right? Just to meet the Nyquist. So that's kind of doing that, right? So we use that to actually control the average sample rate that we need for the application. Okay, so this is a block diagram. I won't go into the detail. So basically, it is very similar to the flash non-uniform sampling ADC. So you can see on the top and the bottom, basically just 2 copy. So one is the coarse, one is the fine. And then we have a timeout logic, as I showed you earlier, right, to control what's the average sample rate. And then we just, again, the output will get the magnitude information and time information. Okay, and that's the diphoto. You can see that, fine, coarse, and then you combine the pulses, and you still need a time quantizer, right? So the same as before. So here is just a little bit of a measurement result. You can see that from flash and subranging, depends on the input frequency. You can see the improvement in the SNDR and SFDR. Just similar to what you would expect, by basically adding a more quantization level. Okay, so that's the flash and the subranging non-uniform sampling ADC. So we kind of focus mostly on the voltage domain, right? And then we kind of ask ourselves, how can we make it even better? And then one of the lessons that we have learned in the past is that, to do that continuous time comparators, it actually it can take extra energy, right, or power consumption, right? Because you need to continuously monitor the signals, right? So the question we kind of ask ourselves is that, hey, to do that comparison, do we really have to do in the voltage domain, right? Can we do in the other domain? And then so this one we were kind of inspired by this so-called this time-based ADC, right? So recently, I'm sure that a lot of you are aware of this so-called time-based ADC, right? So today, people do comparison in the time domain, right? So we kind of ask ourselves, can we do a similar thing, for the non-uniform sampling ADC? So what we did is that, in order to do this time-based, quantization, right? So basically, you do the time comparison in the time domain. We really have to convert the voltage into phase, right? And then this part is just exactly the same of any time-based ADC that we have seen, in our community, right? So we basically use ring oscillators, right? Voltage control oscillators, where you can, convert the voltage into the phase, right? Into the phase or the time, right? Coming out of that ring oscillators. So basically what we are getting is that, if I convert the voltage into phase information, and because we do ring oscillators, right? We do ring oscillators. So we have a different stages, right? Different stage of the ring oscillators. So essentially we are doing this level crossing in the phase domain. So as you can imagine, whenever we have a rising edge on each stage of the ring oscillators, this is essentially doing a phase domain level crossing, right? So I'm still comparing the amplitude, right? It's just that this amplitude is phase amplitude, right? Instead of voltage amplitude. But in terms of the operation principle, it's exactly the same as the voltage domain, right? So as you can see on the left side, right? This is what we have been building, right? In the first 2 prototypes, right? So we are basically comparing the input to the voltage level, and now we are just comparing with the phase level. Okay, and the output, I still would generate a different non-uniform sample, right? Because whenever before, if I cross a certain voltage level, I will send a pulse, right, to generate a point. Same as ring oscillator, whenever I pass a certain level, so which means that the output of the particular stage, it will toggle from low to high, right? So that naturally gives us the non-uniform sample. So that's pretty nice, right? So you can see that, it's basically just, become a zero crossing, right, to that level. And then I can just simply do a comparator in the time domain, right? As we know, if we want to do a time comparator, it's basically just flip-flop, right? Just flip-flop. So I just need to do a flip-flop at the output, and there we go. Then I can have this basically phase domain level crossing non-uniform sampling ADC. Okay, there's another advantage of doing this, which is we call it inherent dithering. One of the issues with the voltage domain level crossing is that when your signals is very fluctuation is very small, right? It can get stuck in between the levels. Then you may not generate any non-uniform sample, right? But however, if that's oscillator, the oscillator will keep oscillating, right? So generally, inherently, it will always generate a sample because you will oscillating, the period waveform will repeat, so we'll keep exercising the outputs coming from that ring oscillator. So that's why we call that as inherent dithering. So even though your signal can be a DC signal or a small signal, you could still get the non-uniform sample. So that's very nice, because you don't need to worry, so much on adding additional dither, which that's what you need to do, in the voltage domain level crossing. Okay, so then what about the signal reconstruction, right? So if we turn that into a time domain, right, and we call it the VCO-based non-uniform sampling modulators, right, and then the output, we still have the magnitude information, we still have the time information. So how do we, construct that, in this so-called non-uniform DSP domain, right? Turns out that they are pretty much the same, except that as we know, because the oscillator is an integrator, so you need to take a differentiation in the non-uniform DSP. Okay, right? Does that make sense, right? So you have integrators, so you have to take differentiation. And it turns out that, with a pleasant surprise, because of these differentiations, we actually simplify that filtering in the non-uniform DSP. So here I just show you a very simple equation. Sorry, I won't go into details. For more detail, please go into those paper that we document a lot more details. So basically what happens is that, if I use the voltage domain non-uniform sampling ADC, as I showed you before, we need the multipliers and we also need adder, right, to do that dynamic FIR filter. And now, if we do the non-uniform sampling in the phase domain, it turns out that because of that differentiation, we just need adder. You basically just add the different sample point of that filter response, and you sum them together, and that's it, right? So we are pretty excited about this. So not only it helps you to simplify the front end to do the time comparison, it also helps you on the non-uniform DSP. Okay, so one question we have been keep getting from the community is that, hey, now you show the equation, we really want to see how complex of that non-uniform DSP. So finally, in 2020, we have the first prototype that we were able to integrate that DSP together with the front end. So here I just want to talk a little bit on this interface issues, because as you can see, the front end is exactly the same thing as I showed you before, right? We do the phase domain level crossing. So the output is going to have some time code, right, coming out. And then eventually, we do want to convert back to the uniform domain, right? So we need to do uniform sampling. So the uniform sampling is actually done here, right? So we have the uniform sampling, we did it in this non-uniform DSP. And to deal with the interface, if those of you have been doing this clocking, right, in the SoC, you have to cross the clock, between different clock domain. We usually, people use this elastic buffer, right? So the FIFO, right? So we did basically the same thing, right? So we will actually use a FIFO, and when we store these non-uniform samples, and then at the output of the FIFO, we would uniformly read out, at the uniform time point. And then and I know this one is not as straightforward, so I didn't go to details. We did spend a lot of time, a lot of credit to Zuben, who's the designer behind this. We spend a lot of time, figuring this out. And you know what? We are right now open source this logic. So if you go to this GitHub site, we have the USC Posh site, and we actually deposit this entire logic right here, right? So how to interface from non-uniform sample to uniform samples, and it's all right there. And feel free to download it, and you can synthesize it, you can play with it, and you can improve it, right? More importantly. Okay, so I just want to show you one thing, right? So now for the measurement for this fully integrated versions. So as you can see, because of the VCO, right? So we have a little bit noise shaping, just a first order shaping. And then you can see that there's a lot of high frequency noise. That's really because of the non-uniform sampling, right? So we actually shape a lot of noise to the high frequency. And then we actually use this non-uniform DSP to filter, right? So we can get rid of those junk. And after we do uniform sampling in the end, we can still get a reasonably good, spectrum, right? So we can get the SNR. So here I just want to mention, the filter that we are doing here. If you ask me, say, Mike, what about we do that in a uniform way, right? Uniform ADC. So we did a calculation. If we are going to do a uniform ADC on this, and to get the equivalent filter response, right? Response, what you are going to end up with, you have to design a 160 gigasample per second ADC. Okay, so that's first thing. Second thing is that you are going to design a 1,537 taps FIR filter. And guess what? That filter has to run at 160 gigahertz. Okay. For us, we didn't think that's possible, but I just thought that it's fun to, make some comparison there. And sorry about this table. I just want to show you only one thing. So we compare this VCO-based non-uniform sampling ADC with the state-of-the-art noise shaping ADC. And we collect the one that has a similar dynamic range, above 70 or around 80 dB dynamic range. The message that I want to talk about here is that you see all the state-of-the-art, they have to use a fourth order shaping. This is using uniform sampling. Now, by using non-uniform sampling, all you need to do is just first order shaping. Okay, so I believe there is still a lot of potential that we can further improve this. So and that's why I'm very excited to share with you guys, right, in the community, and hopefully we can pick up even more ideas. So the question about that non-uniform sampling, the non-uniform DSP. So we calculate the entire non-uniform DSP power consumption, and it consumes about 38 milliwatt, and this is in 28 nanometers. So it's okay, we feel it's okay, but of course it's not 1 nanowatt, right? We are hoping that we can still further to improve this, either through a better algorithm or better technology. So I think there's still a room that we can continue to improve this. But the bottom line here, I want to point out, because of the aliasing profile changes, so there is something that we may gain. Okay, so here, show my my thoughts about why should we consider non-uniform sampling, right? So you can see that non-uniform sampling was hinted already in 1956, right, in the papers, and they talk about the magnitude and time information. And guess what? That's exactly what we have been doing. We just find the magnitude, we find the time. So actually, in my mind, this is a true hybrid ADC, right? So you find the magnitude and you also find the time. So you are not quantizing just amplitude, but also in the time domain. Okay. So why do I think that it's actually possible right now, moving forward? First of all, as we know today, to do the time quantization, if you go to ISACC, you look at JCC, there are a lot of fantastic time to digital converters today, right? Probably because of the technology improvement and also the ideas, right? Innovative ideas that people have been pushing out. You get very, very precise time today to do quantization, right? Even sub-picosecond is possible. Okay. And then secondly, for the Non-Uniform DSP. Now we have a cheaper and faster digital circuit, so there's no surprise, right? More slow, so that will take care of that. And then another challenge for the non-uniform sampling, I believe, was really how do you convert from non-uniform to uniform. So this one, we really spend a lot of efforts, and now we are giving out for free, right? Everything is open source, so feel free to download that. So hopefully, you don't need to worry as much about this, sample conversion. Okay, so what are the potential, non-uniform sampling ADC moving into the future? So here, at least in our group, we kind of experiment on the flash, on the subranging, and also on the VCO base. And I'm hoping that there will be more, out of this. And then just one word about this asynchronous RADC. So, this is one of my favorite ADC topology. I just want to say that one is still uniform sampling. So it is not yet a non-uniform sampling. So if you have any idea how to turn that into that, I'll be really happy to see that. Okay, so now I'm going to change gear to go beyond ADC, right? So far I've been really focusing on ADC, and but as you know, the sampling can be really universal, right? ADC is not the only circuit block that actually use sampling, right? There are many other blocks. So how can we do that? So we kind of went ahead, right, and go beyond the ADC block, right? So this is our ADC block. And in this case, we really try to go to the entire receiver. Okay, as you can see here, the conventional receiver, you receive the signal from antenna, in your filter, you probably gain, you probably down conversion, and do more filter and do the ADC. So now, if I can do a little bit of non-uniform sampling ADC, right? What if I can push this filter, to this non-uniform DSP domain, which I kind of show you in earlier slides? Then maybe I can actually try to relax remaining filter requirement upfront. And I think that this actually can be quite important because, today, if you open up your cell phone, there are tons and tons of filter, analog filter, right? And those are super expensive, right? Those filters probably occupy a lot more space than the actual radio chip, right? So filter is actually a very important problem. And I believe this is really something that, so-called non-uniform sampling can actually help. A filter problem, maybe we can do offload, right? Something to this non-uniform DSP domain. So that's what we have been trying. And the way that we try is that, we try to apply to this subsampling front end. So I think many of you probably are familiar with this, right? The subsampling is nothing new, right? So you can subsample the signals, right? And because of frequency aliasing, so you can see the frequency aliasing here, you could actually down convert passband signals, right? The passband signals, because I'm just using one of the integer multiple of the fs to down convert the signal, right? To do the subsampling. The problem with the subsampling is that, hey, because of those aliasing right there, right? All the spectral aliasing, because of uniform sampling, unfortunately, if you have some unwanted signal happen to be at those aliasing band, they're also going to alias back to your signal band. So that's really bad, right? So that's why conventional subsampling front end, they also need to use a very good bandpass filter. Okay, so what about non-uniform sampling, right? So as you can imagine, if I use some kind of non-uniform sampling, so in this case, I'm no longer using signal dependent. I'm actually carefully design that non-uniform sequence. Okay, so this is just another type of non-uniform sampling, right? So I can do signal dependent. I can also do signal independent, right? So this is signal independent sampling. So I can actually engineering this sampling sequence. As you can see, I perturb this sampling sequence. And you know what? I can also perturb that aliasing frequency profile, right? So you can see I can actually preserve the aliasing at the desired signal band, right? And at the other band, I can actually reduce those aliasing, energy, so that you see this. Even though there's a blocker right there, right? If that's uniform subsampling, it's gonna alias a lot, back to baseband. But now because I can engineer this sampling sequence, I can actually reduce a lot on this amount of aliasing. So that's very good, right? Because you can actually retain your signal at a much better SNR, right, or SNDR. Okay, so basically that's what we did. So we actually went ahead and built a millimeter wave receivers. And as you can see, the way that we did is that from a conventional subsampling receivers, you need a very good bandpass filter, and you just subsample, right, at the uniform clock time grid. So all we did is just that we changed the clock, right? So we changed the clock, and then we also relax that bandpass filter, and that's it, right? And then we do the sampling, and then we do that, non-uniform DSP that I talked about, right, in the ADC domain. So look at what we got, right? So here, the spectrum that I'm showing you is that, the prototype, we can program that into uniform subsampling or non-uniform subsampling, right? So which is shown in red and blue. So you can see that, once I activate the non-uniform subsampling, I can reduce that aliasing by as much as 29 dB rejection. So that's kind of interesting, right? And then we also did another test within the modulated signal, and we show a blocker at that aliasing band. And as you can see, if I do this uniform subsampling, it's a mess, right? If you look at the received constellation, it's a mess. You cannot do anything. And now if we turn into non-uniform subsampling front end, now we can start to see the constellation, right? So because we can actually reject that aliasing by that 29 dB. Okay, so that's on the receiver side. And just before I conclude my talk, I just say one more thing, right? So far, I pretty much focus on non-uniform sample, the input signal, right? So the ADC or the receiver, I always focus on non-uniform sample, the input. But nobody said that we have to only focus on sampling the input, right? Can we non-uniformly sample something else? So so Shuo is the designer behind this, right? So he actually was saying that, hey, you know what? Why don't I non-uniformly sample the filter response? So as you can see here, you can imagine this is like a level crossing quantizer, right? And then instead of sampling the input, I'm going to sample the filter response. So here, for example, he's trying to synthesize the impulse response like this, and then he's going to do the comparison with this triangle wave. So as you can see here, basically what we are doing is that we are non-uniformly sample the filter response. So you can see this red cross point, right? So from those sample points, we turn into this non-uniform waveform, right? And then if you look at the frequency response of this non-uniform waveform, right, it actually get pretty close to the original filter response, which is shown in the blue, right? So you see there's some deviation just because you do this non-uniform sampling. You're gonna increase, you're gonna have some quantization errors, especially these only 2 level, right? But by and large, you see it's fairly close. So basically, what you can get is that it is a non-uniformly sampled filter response, and to mimic some desired filter response that you're trying to do. Okay, so that's kind of interesting. So then the question is that how do we use that, right? So one of the idea that we had is that why don't we do that in the transmitters, right? So shown on the left, these are conventional transmitters. You have a signals and you have LO, right? A signal, and it's a uniform waveform, right? And you up convert to the desired signal band and you transmit to the antenna. So now what we're gonna do is that we are going to multiply this uniform LO waveforms, right? The clock waveforms with this non-uniformly sampled filter response. So then guess what? Once you do this operation, you would actually create an equivalent bandpass filter around that center frequency of that LO. So that's very interesting because basically what we are saying is that you can just turn a conventional transmitters, and you don't need to change other clock. All you need to do just to change your LO waveform, right? So in this case, as you can see, all you need to do just turn that uniform LO waveform to this non-uniform LO waveform, right? And then you can still upconvert to the output. And then because of this additional bandpass filtering right here, you could actually relax the remaining reconstruction filter in the analog domain. So you can see that by doing this non-uniform waveform for the LO, you can actually relax the analog filter in the analog domain, right? So this is actually a similar story to the receiver. Basically we're trying to help out our colleagues, right, who is designing the filters, in the analog domain, right? So they can relax their spec. Okay. So this kind of topology, we call it the time approximation filter, TAF, because we really try to approximate in time, right? So remember, the non-uniform sample is really to get the time information, and I think that one of the beauty I really like about this is that it's simple, right? So compared to the conventional semi-digital FIR filters, you just use one slice and it's mostly digital, and all you need to do just to change that mixing waveform, and that's it. So here are some of the prototype that we were able to measure, right? So we were able to change the different LO waveforms, and as you can see, we can achieve a different filter response, just by changing that filter response. Okay. So earlier this year, Shuo, further extend this idea. He basically saying that, okay, so far the TAF filter was using one level crossing quantizer, right? And he's saying that, why don't I use two, right? So if you're ADC designer, you can think of this as like a 2x oversampling, right? So I use two quantizers to double the sample on that filter response, and that's exactly what he did. So as you can see here, we call that as a tri-level TAF filters. So just using these two non-uniform sampled filter response, and we still modulate that LO waveforms, right? And then we send to the same transmitter architectures, right? And the output, we were able to actually use that property of the filters to get a really low noise floor. As you can see, it's minus 169 dBc per hertz. And know that we did not use any SAW filter, right? And just by using this non-uniform sampled filter response, and we can get this kind of a response. Okay. All right. So let me conclude my talk. So hopefully, today, I show you a few examples, from ADC to radio transceivers. And I think the message here is that, we can perturb the sampling time in a weird or funny way. And I believe it may present some interesting opportunity for the future circuit design. Okay. And secondly, I wanted to point out that, I believe there is still a huge room for the human designer to create. And I believe this is not replaceable by the AI or machine learning. I know a lot of people are talking about this today, and indeed they can do certain things. But I think, to create a room like this, I think that still ultimately rely on the human designers. Lastly, I'd like to say that, let's go noosing, right? Not fishing, it's noosing, right? So let's do, think about non-uniform sampling and how that can perhaps transform the block that you're designing today, right? So maybe there's some interesting opportunity. Lastly, I do like to thank all my students. I think without all my fantastic students right there, Zhufen, Xu, Chenru for the former student, and the current students, Si, Mustafa, Sumya, Aoyang, Masarat, without you guys' efforts, I'm not presenting any of this, right? So it's all their works. And then of course, I would like to thank our sponsors, and I like to really especially thank Dr. Mark Rich, because of his vision. He supported this non-uniform project, from the very beginning, and the entire Google R2 teams. And I also like to thank the current sponsor from Dr. Hancock and Mr. Olofsson and Leaf for the PASH programs, and also the NSF sponsorship. So with that, thank you for your attention, and I'll be happy to take a couple questions.
Hi, Mike, can you hear me?
Yes.
Okay, great. Yeah, my name is Alvin Loke. I'm the webinar chair for the Society, Solid State Circuit Society. Hey, Mike, thanks so much for a very, very enlightening talk. So we've got a bunch of questions come out from the Q&A, and if you have questions, please keep asking them. So one question I did have was, can you comment on how you would generate the sampling sequence for the non-uniform sampling subsampling front end?
Sure. That's very good questions. So let's go back to this one. Yeah. So this one, we actually use this gradient descent algorithm. So we actually, try to first look at what's the ideal frequency response that we're trying to generate, right? So we have some initial, so based on the calculation, because you could actually calculate. So remember that this FFT, right? The frequency ADC, you could actually do the FFT of the sampling sequence exactly the same way as you do for the uniform sampling, right? So you have those sampling trend, the delta trend, and you do FFT on that, then you can get a frequency ADC spectrum. So you can do that. You can mathematically calculate what's the relationship, between the time sample to the frequency ADC profile. So what you do is that you can actually start with some desired profile, and then you look at that FFT relationship. So you can kind of hand calculate, right? You can calculate what was the shape, but it probably cannot get exactly what you wanted. So then what we did is that we actually do iterative algorithms, it's like a gradient descent algorithms. So we actually start from that hand calculated time points, and we start to perturb, right? We start to adapt and say, hey, for example, I really want to knock down this ADS energy, right, at these particular frequencies. So by doing that, we can really get the optimum sequence, right? So it's actually a combination of the analytical analysis and plus this numerical optimization. So it's both, right? And then by the way, this is one of the things that I think this AI machine learning algorithm can actually help, right? Because you could actually use machine learning algorithms to help you to fine tune this sequence, this non-uniform sampling sequence, so that you get the profile that you're really hoping for. Okay.
Looks
so
like these techniques are particularly amenable to like the advanced technology nodes where you have a lot of access to a lot of quote cheap digital, right, for computation, right?
Correct.
So
Correct.
yeah, great. So next question: when you say average sampling rate, is the instantaneous sampling rate allowed to go below the Nyquist rate? Does that not mean there is more aliasing that INS non-uniform sampling introduces? Is this still possible to recover all information?
Yes. So yeah, so the average sample rate, right, which means the instantaneous, right? So if we can, let me see, go back to this, right? So as you can see, right, so that's exactly what they already point out in 1956 paper, right? So so within so first of all, you do have to chop into interval, right? So whatever, so basically what you do is that you look at what's your maximum frequency. Okay, so let's say how about your maximum frequency is 1 gigahertz, right? So basically what they are saying is that you have to first divide into one the interval of half of that, right? So means that sorry, so that should be right. So 1 gigahertz maximum frequency is 1 nanosecond, right? So that means that you need to sample at least 2 gigahertz, right? So that means that every half nanosecond you should have at least one sample, right? So if you go for the uniform version of the Nyquist sampling, so we know that every half nanosecond we have to take a sample, right? So what this is saying is that you don't necessarily need to do that. So long as within every half nanosecond you have a non-uniform sample right there. Okay, so you're right. If you don't have a sample there, there could be a aliasing, unwanted aliasing at some point. But so long as you ensure within that half nanosecond, you have at least one non-uniform sample that to represent your signals, magnitude and time, then you will be okay, right? So I think this paper actually is summarized very very well. So that's why later on you remember that the example I show on the subranging non-uniform sampling ADC, where we use the timeout to control that average sample rate. So that's also for that reason, right? Because we got to make sure, within a certain time interval, we can at least have one non-uniform sample get generated.
To answer that question, then the instantaneous sampling rate cannot go down below the Nyquist rate, or at least the content of the information. Yeah. Okay,
Correct.
great. Okay, so next question. What happens if the input frequency is small and the harmonics fall out inside the cutoff frequency of the digital AAF?
Right, right. So, so if that's something that you cannot really filter out from that filter, right, that we did in the NU DSP, there is something that you can do, related to the signal reconstructions, and this is like interpolation. Okay, so here most of the work that we have been focusing on is using the zero order hold. So this is probably the most crappy interpolator, right? Because you're zero order hold. But it doesn't mean that you cannot use a higher order interpolation technique, right? And also, in fact, remember I mentioned about some researchers in the signal processing societies. They actually propose a lot of interesting different interpolation techniques or iterative algorithms that you can actually reduce that errors that due to that non-uniform sampling, right? So basically, how you reconstruct the original signals. So there is another tool that you could use. We did not, spend too much effort, focusing on those. But I can assure you that there's a huge body of the research and also potential there. You could use, just in case that, hey, if you say that it's already invented, it's nothing that I can do with the filter in the NU DSP, then that's where you can go, right? In fact, I believe that we have to try out a couple interpolation algorithm, and we do see an improvement for that.
Got it. Question. Are the non-uniform time sampling positions continually adjusted? Is this a source of error?
Yeah, so that's pretty good questions. So there are a couple of things, right? So if you are using this signal-dependent sampling, right, like this, so as you can see here, we always generate a pulse, right, whenever the signal crosses a certain levels. So those time is exactly time dependent, right? So whenever I cross the level, I just generate a sample event, right? So there's nothing that we can control that's really generated by the input. However, there is something called time quantizer, right? So as you can imagine, in real life, we cannot really quantize that time with infinite resolution, right? So because we just really cannot tell that, okay, it's happened at 12.56789 seconds, you generate a sample, right? So in the end, there's gonna be a finite resolution. So ultimately, that time will be dictated by these time quantizers. Depends on how fine you can do this. Now, as you can imagine, if I cannot do very fine, right? So that will introduce some quantization errors, right? So that quantization is real. So it actually can, affect the fidelity of your reconstructed signals. So for that, I would encourage you to read this expanded paper. We actually document a lot of analysis on how that finite time quantization can affect our signal SNR, as an example, right, or SFDR. How would that affect? So I would encourage you, to go into more if you like to have more details. So we actually document some of the analysis and simulation right there.
Got it. To a related question, previous block diagram with all the flash ADC, for instance, at the front. I mean, there's latency in basically generating the time quantizer samples or the strobing, right, of the data. I mean, does this have what impact might this have on like the data rate or the sampling rate which you can process the samples?
Right. So that's a very good question. So the comparator by itself, indeed, there's be latency, right?
Yes.
A bit latency. So that latency, so long as everybody has the same latency, it doesn't really matter, right? Because you just delay. You can imagine that all the non-uniform sample, they just horizontally shift by delta t, right? The delta t can be 1.5 seconds. Yeah. But however,
It's being sampled by a corresponding latency, and you're fine, right? You're tracking that latency. Got it. Got it.
Exactly. But here I do want to point out that the mismatch between them that become important, right? As you can imagine.
Yes.
Right.
Yeah.
Yeah.
Got it. Can you comment on the connection between what you've presented and continuous time digital signal processing, which the person asking the question was proposed by Professor Civitas, who apparently is in this call in the early 2000s. In his work, aliasing was avoided by quantizing upfront.
Right. Sorry, Alvin, is the question about the difference or?
Yeah. The connection between what you've presented and continuous time digital signal processing.
Sure. I believe the biggest difference is that, the thing that we have been going after is that, we really try to convert back to uniform samples, right? The continuous time processing, as I pointed out earlier, that, whenever they have this pulses, the sample events get generated, they actually combine in an analog fashion, right? So you actually combine those pulse energies, and the output, is still analog-ish, is coming to the asynchronous waveform, as you can imagine, right? If you just sum up those non-uniform sample points. So here, what we really try to do is that we like to make this non-uniform, so-called non-uniform sampling ADC looks just like a conventional ADC. So if you are a user, right? So you say, hey, I just want to buy this ADC product. I want the output to look exactly as the same as the conventional ADC. So it means that the output should always give me the uniformly sampled digital codes. Okay, why? And as I mentioned earlier, because I really like to use that DSP and a processor to actually to process those samples, right? So I think that I believe that that's a key difference, right? That you can use that in this internal non-uniform signal processing, so that you can do, in this case, it's filtering, right? You can do the filtering and eventually turn that into uniform samples. And I think that's really something that we are going after, because the way I like to think about this is that I like this to be globally uniform sampling, right? So on the top level, globally it's uniform sample, but internally or locally it's non-uniform sample. So that's really the efforts that we are going after. However, as I showed you before, you remember that in the flash ADC case right here, you see that there's a post generator, right? And then I need to send that to time quantizers. So maybe that's a little bit linked to the continuous time DSP, because I recall, if I recall correctly, right, they also use a lot of delay, to process those non-uniform events, right? So I think some of the circuit technique that you use in the continuous DSP, you could actually apply that to this post generator, at least in this domain, right? So how you make the time precision more accurate, to be more precise, and as I mentioned earlier, right, the matching between these different paths is also important, right? So how do I make sure they would match better, between the different paths? Those are very interesting questions, right, to actually go after.
Got it. Next question. Can you comment on the clock jitter with uniform sampling, like a power at millimeter wave frequencies?
Right. That's actually a fantastic question. We also ask ourselves many times throughout the project. By the way, I just want to point out that when we work on this project, nearly 10 years, I believe we failed more than what we succeed. We tried. So today, I already showed you a few points, but I can tell you we fail every day, right? We fail every day. We look at this. I think one of the thing is that we are too used to designing a uniform sampling ADC, so I naturally try to apply whatever that I know about designing the conventional ADC. And you know what? It may not be true for the non-uniform sampling. So I think that's like one thing has double side, right? So it has opportunity, but that's also something that you should think about. Okay, so go back to the question about the jitter, right? So we believe that especially we are subsampling on the millimeter wave signals. As you know, the phase noise or the jitter can also get down converted, right? And then that will be also proportional to to the input signal frequency. So in this manners, I believe there's no advantage, between non-uniform and uniform sampling. In fact, we actually compare the SNR using the same clock source between uniform and non-uniform, and we get a very similar SNR. So I think the answer is that we don't have advantage. We also don't have disadvantage. So that's basically the same as uniform sampling. And I think the reason is just because eventually you are still down converting from that particular frequency, right? That you try to ADS down to do the down conversion, right? So you still need to use a clean enough clock to do the down conversion. And by the way, just to let you know, right? If let's say you say, hey, why don't I use a heterodyne receiver, right? And I just down convert these 27 gigahertz signals. And sure enough, when you design that LO for that mixer, right, to mix down, that one also has the same, phase noise requirement, right? Just because you try to down convert. So that's why I think that, in terms of the clocking, unfortunately, there's no saving here, right? It doesn't matter use uniform, non-uniform, or the conventional architectures. The clock still remain a interesting block to design, right, or challenging block to design.
Got it.
So I hope I answered the question.
We've got a lot more questions. I think in the 3 minutes we have left, we probably can only take a few, because I'll just continue to go by the order in which I received it. So it looks like someone's going to try to go deeper into this, follow your work. If I have a set of non-uniformly sampled time amplitude pairs in MATLAB, is there a method or function to calculate something resembling an FFT spectrum from these value pairs?
Right. So that's a good question. So what I suggest, and that's also what we did in our group, is that first of all, because you are in MATLAB, you could actually do crazy oversampling. Okay, just oversample a lot, to crazy high frequency, because in MATLAB we have the privilege to do this. And the good news is that because you sample at such a high rate, those aliasing, they are happening at crazy high frequency, which you probably don't really care anyways, right? Then you can just use the FFT in the MATLAB to help you to examine what's the difference, between different non-uniform sample, right, with different magnitude and time functions. So we kind of think that's the a quick, easy way to start investigating in this area in general, right? So yeah, so that would be my advice. And then later on, that would be similar to how you design the ADC. Then you start to do the non-ideality modeling and things like that, right? And feel free to go to the GitHub, as I mentioned earlier. We really try to help people. I just look at this 1956 papers, I just don't understand why non-uniform sampling is just not nowhere compared to uniform sample, right? So and I think because of technology scaling, as Alvin you just point out, I really think that we have a shot here in our generation, right? You look at the latest iPhone, close to 11 or 12 billion transistors that we can do today. I think this environment is different. I think there could be something that we can investigate in our generation, and hopefully, we can see a more exciting and interesting, work, in this area in general.
Yeah. It would appear that your system is perfectly linear, as all harmonics will be filtered off while it isn't. Shouldn't it be better to do the calculations on slides 7 and 8 using some other signal, for instance, a multitone?
Let's see, slide 7.
Yeah, slide 7, 8.
Right. How we do? Yes. Here I just this is for conceptual. That's why I like to use a single tone as a illustration. In real life, yes, we do multi-tone. We even do modulation signal, right? We even send the OFD, and that's kind of a modulation signal. So yes, so there's gonna be some intermodulation, things that can be related to the linearity. So in terms of designing the circuit to be more linear, so I think that's part, you can just borrow the conventional wisdom of how you design the your ADC or your receiver. I think that part I don't find too much different. However, I do want to point out a little bit related to that what I mentioned earlier about this interpolation, right? So far, we mostly focus on zero order Holt because that's the easiest, crappiest, and simple interpolation. If you are able to use some of those iterative algorithm or your higher order interpolation algorithms, you could actually, also further reduce down those distortion, due to that interpolation, basically. So yeah, so I think, yeah, so if you want to have absolutely linear systems, so, probably going after both, right? So, linearize that in your circuits design, designing a better sampling circuits, your ADC, right? In this case, probably mostly on the sampling circuits, right? And also, how you get the better interpolation, algorithms that can both help.
Got it. And just to wrap up, in the interest of time, last question. Could you comment on the effects of the nonlinearity of the VCO?
Sure. Yes, I didn't get a chance to talk too much. So thanks for asking this question, because in fact, as we know, this VCO is nonlinear, right? So we actually calibrate that VCO linearity inside this non-uniform DSP. And we actually found this quite interesting, because now we represent the signal in magnitude and time domain, right? So magnitude and time functions. The calibration actually can be quite interesting, right? Because this is different from conventional VCO-based ADC that you can only calibrate in the amplitude domain or magnitude domain. Now you can also compensate in time, right? Because this time you will dequantize it, right? so we actually so for that, please go to the paper, and hopefully we're gonna have a more expanded version in the journal papers. So please go ahead and read those journal papers. We actually talk a lot more detail on how we actually calibrate the distortion of the VCO.
Got it. Okay. Hey, thanks again for an awesome presentation, Mike. Obviously, there was no shortage of interest. I apologize to those whose questions did not make it and get to be asked in the interest of time. Thanks again, everyone, for attending. Hope everyone stays safe and well through these times. For those of you in the US, don't forget to vote. That's very important. I did want to say thanks again, Mike. This presentation will be made available in the SSCS Resource Center, as well as on YouTube, which we'll be posting. Okay. So with that said, there will be a survey that will be coming up at the conclusion of this webinar. If you can please provide your inputs, suggestions for future topics, that would be great. Thanks again. Just a virtual clap for Professor Chen. Appreciate your time, and we'll adjourn for now. Thanks. Have a great rest of the day.
Thank you. Thank you.